It's a great pleasure to be here. Thanks Michal and Martin for inviting me, for arranging this event. And of course, this event is happening thanks to Mike and Eric. And I have had a fairly long association with Eric. I think we first met 22 years ago, and that was in Chennai. And this morning during some of the talks, I was actually counting. It turns out that Eric has been to India oftener than I have been here. This is just my second visit to Rutgers. So even though we've been collaborating for a long time over the years, it's been in India, and we've also been meeting often in Europe, and it's been a great pleasure. But it's not just the collaboration. I think at the time when we first met, I had just started doing complexity theory, and I think my interaction with Eric, it was, he didn't mean it to be that way, but it was like a kind of mentorship. It gave me immense confidence that I can do something here. And over the years, I find that my PhD students also, even before they had met him for the first time, they had a certain, there was an aura around him. And then when they met him, like here's this guy whom we have heard so much about, and they did not need to be in awe of him. So that was very wonderful, the feeling that came out of that. So I'm very proud to count myself as one of Eric's collaborators, and I'm happy to equalize US trips with his India trips, and I hope that we will be able to meet again on several such occasions. I have not interacted that much with Mike, but I think we first met again on that one previous trip to Rutgers, and I've enjoyed reading some of your work, and not at a personal level, at an academic level. So I hope that there's a lot more of productive work coming from both of you. Okay, so let me get on with my talk. I'm going to talk about some work in algebraic complexity. This is work that I've done with my former student Nitin Saurabh, and this is work which large parts of it indirectly trace their influence to Eric and to what I learned from him about many of these classes. So I remember at some point when people used to ask me what kind of complexity I do. Do you work on this NP, NP? Do you work on D? And I kept saying, no, I work inside P. And that inside P phrase I definitely got from Eric. So this is work which is inside algebraic P, and okay, let's see as we go along the kind of questions that we're going to look at. So the outline of this talk is I'm going to talk about natural polynomials which are complete for algebraic P, and in this talk the V everywhere is Valiant, and Valiant initiated the study of these algebraic classes, so I just take standard Boolean classes and prefix them with a V to get the algebraic class. So I'm going to talk about natural polynomials complete for VP. I'm going to talk about polynomials which have intermediate complexity, and I'm going to also look at the notion of monotone projections as a reduction, and discuss a few lower bounds, one particular lower bound in that setting. So yeah, let me start off with some very basic stuff. The objects of interest in this talk are polynomials, and in fact families of polynomials. So we fix some field and we have an unending supply of variables, and we can build up polynomials using these variables. And like I said, we are going to talk about families of polynomials. So the nth polynomial of the family is the polynomial Fn. For instance, here I've listed out a few: the linear polynomial which just adds up n variables, the monomial which multiplies n variables, the determinant of an n cross n matrix where every entry is a fresh variable, or you could add up polynomials and take their powers. So these are examples of families, and we are going to be interested only in what we call P families, polynomial families. So the number of variables as well as the degree of the polynomial should not grow too fast. It should grow only polynomially with n, and that's one reason why the last polynomial there is going to be knocked out. We are not interested in such polynomials at all, exponential degree polynomials. Okay, so with P families, what is the kind of stuff that we are looking at? Well, the computation model we need to fix first. So here's the simplest computation model one could think of: a circuit. It's a directed acyclic graph. At the leaves you have the most primitive polynomials, which are a single variable or a field constant, and then you combine them in the obvious way using addition or multiplication. So at the output node out pops some polynomial. Okay. You could also have branching programs which are also directed acyclic graphs, but now you have labels on the edges, and somehow implicitly every node is doing a collection of polynomials. So you can talk of the polynomial between a pair of nodes, and this polynomial is what is defined here at the bottom. For a pair of nodes uv, the polynomial computed between uv is defined like this: look at all paths from u to v. For each such path, look at all the edges along the way, multiply all their labels, you get one monomial, add up all these monomials to construct the polynomial. So for any pair of nodes in this graph, there is a polynomial computed between them. Okay, so now here is category of a list of various complexity classes in the algebraic setting. We would be looking at polynomial sized branching programs, polynomial sized circuits. So, given the two models that I just described, these are the obvious classes. Polynomial sized circuits is really what Valiant described in way back in 1979 as the algebraic analog of P, and Valiant also described an algebraic analog of NP. So, that is this definition down here, which is that you take some polynomial g which is in VP, and then you have some of the variables of g which are reserved, you sum up over all Boolean instantiations of that. So, you get a resulting polynomial in the x variables, and that is this polynomial f, which I am going to say is in VNP. So, it is an exact analog of the statement NP is equal to there exists dot P. So, when I first saw the definitions of these classes, I think this was at a talk that Manindra was giving in some place, and so he had this definition of VP and VNP, and then he said that look, VP we are looking only at P families. So, there is this restriction of polynomial degree, and I remember almost jumping out of my seat saying that's not P, that's log CFL, that's log. So, we had a lot of discussion about log CFL, SAC1 in my earlier discussions with Eric and Vinay and a couple of others. So, I still think of VP as really the analog of log CFL, and in many ways that is really the correct description. Anyway, these are the complexity classes that are going to be of interest to us. What kind of polynomial families can be computed by these classes? In particular, what can be computed in VNP? It's easy to give canonical examples here. Of course, everything in VP by definition is in VNP, but here are some very standard Sharpe complete problems, and you can see that an algebraized version of them is in VNP. The Hamilton cycle polynomial. You consider a complete graph on n vertices, and every edge has a new variable. So, then for each Hamilton cycle, you multiply the variables appearing on that cycle, so that gives you one monomial, you add up all these monomials, that is the Hamilton cycle polynomial. Similarly, you have the clique polynomial, you have the permanent polynomial. The permanent polynomial is of course very well known. The others are algebraic versions of the Boolean problems which are well known. Why are we interested in looking at these classes, VP versus VNP? Well, the algebraic classes, it turns out that we need to separate them in any case if we want to separate P from NP. I certainly believe that P and NP are not the same, and in order to get there, which is still very far away, I think, we would first need to prove that VP is not equal to VNP, modulo some assumptions. But there is some reason to believe that separating these classes may well be easier than separating P from NP, because the model, although it appears at first glance to be much more powerful, you are actually doing algebraic computation, you are putting together monomials which carry all the information about this problem, but you are also limited in what you can do with the individual monomials, how you can tweak these polynomials. You can only add and multiply, you can't do anything else. So, in some sense the model is weaker, and we have more mathematical tools because we are dealing with algebraic polynomials. So, that's a very good reason to look at this question at all, the VP versus VNP question. So, how do we compare families of polynomials? There is a whole bunch of families of polynomials which we know are in VNP, we do not know that they are in VP. There are various other families which we know are in VP, and we would like this notion, like to say that some polynomial family is harder than some other family. So, we need a notion of comparison, and the most standard notion would be projections. So, we say that f is a projection of G if it is possible to compute G, if it is possible to compute f using a circuit for G with no extra gates. So, take that circuit as is and just change what you feed in at the inputs. So, whatever were the variables for G, you instantiate them with the f variables or field constants. So, that is just a projection, but in particular, since we are dealing with families, we would be interested in projections which are not too large. So, a P projection allows you to obtain the family f from the family G if to obtain the nth polynomial Fn. I do not have to look at the nth element of the G family, I do not have to look at Gn, I can look at Gm, but m should not be too large compared to n. So, then that is a P projection. If I allow to m to be slightly larger, maybe quasi polynomial, that gives me a QP projection. Okay. So, now the big open question in this setting formulated right in 1979 by Valiant is, can the permanent be obtained as a P projection or even as a QP projection of the determinant? These are two very well known polynomials which we understand very well, and can we say anything about this comparison in this sense? So now the first question which I want to address, which I want to describe about is what are natural polynomials which are complete for VP. So we have a notion of comparison of polynomial families, and then we would like to understand what is the hardest polynomial there. And in particular, understanding the hardest polynomials gives us some more insight into how that class itself behaves. So here's a list of some known completeness results for VNP. All the VNP polynomials that I mentioned earlier, which arose from sharp P kind of problems, Hamilton cycles, cliques, permanents, they're all complete for VNP under polynomial projections. So one would expect that since the question of VP, VNP was posed as determinant permanent, therefore determinant should be complete for VP. And indeed, the determinant is complete for VP, but via QP projections, not P projections. So that's not satisfactory. And in fact, if you are going to allow quasi-polynomial projections, then the determinant is even complete for a larger class of quasi-polynomial size circuits. So the fact that determinant is not really complete for VP under polynomial size reductions led us to start looking more closely at what exactly is it that characterizes VP. For VBP, for branching programs of polynomial size, we again have complete problems, and in fact the determinant is complete there. So the determinant really describes branching programs. So the question that we were interested in is what describes VP the best. So it's like the question of the difference between branching programs and circuits of polynomial size. Okay, so one thing to notice is that monomials of complete polynomials are enumerating natural combinatorial objects in that list before. So Hamilton cycle, clique, permanent, paths. So the iterated matrix multiplication was the last polynomial family there. Each monomial corresponds to a path in a certain directed graph, and each monomial in the associated polynomial corresponds to a different path. So as you enumerate all the paths, you put them together, you get the polynomial. So this is a kind of rule of thumb that you have a problem which is counting problem which is complete for sharp P, then a natural algebraic version you would expect it to be complete for the algebraic class. You have a counting problem complete for sharp L, then you would expect that the natural algebraic version would be complete for branching programs. So this very naturally leads us to this question of what is it that we should be enumerating if we are looking for completeness for VP. So we need some combinatorial problem which, when you're trying to count it, it is complete for the associated counting class sitting behind VP, and as I said before, the associated class is really sharp log CFL or counting past trees in some context free derivation. And then you want to algebraize that and say that the corresponding polynomial is complete for VP, but it sounds like a very murky roundabout way of doing things. So what was known till now about VP completeness? Actually very little. So Bergesser had shown that some very generic polynomials which literally describe the generic computation of a polynomial sized homogeneous circuit, these are complete for VP. And there's no surprise there. I mean, they're kind of describing what the class is. So you pull out a family which describes the class, then of course this family will be complete for that class. So as a proof of concept that this class has complete families, it's fine, but in terms of giving more information about the class, this family is not very useful. Later, Ranraj showed that using this depth reduction which is known for this class, you can describe what are called universal circuits. There's a more detailed exposition in the survey by Shpilka and Yuhodov. So these universal circuits are also in some sense generic polynomials arising out of generic but depth reduced circuits, and these polynomials are also complete for VP. Again, they don't give independent information about the class, they describe structurally what you can do with the class. So this is what was known, and we were not happy with this state of affairs. So that's where we started looking for more natural polynomials which I can define without recourse to how the class VP is. Somehow I should be able to define the family independently and then show, hey, look, this independently defined family is complete for that class. So we had some success a couple of years ago along with a bunch of others on an Indo-French project. We showed that certain kinds of graph homomorphism polynomials were complete for VP. And this result, it really should have answered the question which we were looking for, except that it required oracle reductions. So to really tightly characterize the class, P projections is the way to go. So we continued tinkering and hammering away at this, and this is the result which I would like to describe a little bit now. A variant of this, in fact a cleaner version, so maybe I should call that a variant of this, a certain kind of graph homomorphism polynomial which is in fact complete for VP with respect to P projections. So I want to describe what this family is. Okay. So this is an enumerator polynomial, which means that it's a polynomial, each monomial of which is going to correspond to some homomorphism between two graphs. So let's fix any two graphs, G and H. What's the homomorphism from G to H? Is just a way of mapping the vertices of G to the vertices of H. This mapping does not have to be 1-1, it can collide, allow vertices to collide. The only restriction is that it should preserve adjacencies. So if there is an edge u v in G, then whatever u maps to and whatever v maps to, they should be adjacent in H. That's a homomorphism. So it's not an isomorphism in particular, so non-adjacencies do not need to be preserved. Non-edges can get mapped to edges. So now with the way we're going to, sorry, yeah?
Are there loops on these graphs or they no?
We could allow loops, it doesn't matter.
Okay, so, but if you have two guys that map to the same vertex,
Yeah.
then there has to be a loop on this guy.
If they are adjacent,
If they're
yes, absolutely. So if adjacent vertices map to a single node here, then the loop is absolutely essential. And in fact, once you have a loop, then of course there is always a homomorphism, but we are going to enumerate homomorphisms. So yeah. So now the way we will pull out an algebraic version of this is to say that we are looking at homomorphisms from G to H, and in the graph H, we are going to plant a new variable on every edge. So I have these variables yij is on the edge ij of the graph H. Now I have this sum, so it's an enumerator polynomial, so there's a sum over all homomorphisms. Take any homomorphism phi, and now take every edge uv in the graph G. Because this is a homomorphism, the image of uv, there's phi u and phi v, two vertices in H, they must be connected by an edge, and therefore there must be a variable with that name. So take that variable. Now do this for every edge in G, collect all the corresponding variables and multiply them out. So that gives a monomial which corresponds to this particular homomorphism. And now we add up over all homomorphisms. So this is how we come up with an algebraic polynomial corresponding to a homomorphism, corresponding to homomorphisms between two graphs. Okay. Now what more can we do with this? We want to come up with VP completeness, so it's not enough to have two graphs, we need families of graphs corresponding to different n. So we will look at P families of graphs. So a P family, again the number of vertices in these graphs should not grow in a wild way, it should be controlled polynomial in n. And then my polynomial family Fn, the nth polynomial is the homomorphism polynomial between the nth G graph and the nth H graph. Okay. So this is now just a description of a homomorphism family. Now we have to see where the completeness is going to come from. What G and what H should we take so as to get nice properties. Okay, maybe just to illustrate this definition of the algebraic homomorphism polynomial, let me give a quick example. The graph on the left is G, the graph on the right is H. Here's one homomorphism, A to U, B to V, C to Y, D to W, and it gives rise to that monomial there. Here's another homomorphism, which in fact allows some things to collide, it gives rise to a monomial. So notice now that the homomorphism polynomial need not be multilinear, there can be lots of collisions. The same edge could be used to correspond to different edges in G and so on. Here's a homomorphism which just uses the same edge 4 times and so on. Okay. Now to put this to use, we are going to use some nice properties about graphs which do not have homomorphisms. So in particular, we say that a graph A is rigid if there is no non-trivial homomorphism from A to itself. Okay. Almost all graphs are rigid, so that's good for us because we are going to need to find such rigid graphs. The only homomorphism from A to A is the identity. These are rigid graphs. We'll also talk about two graphs being pairwise, being incomparable with each other. A and B are incomparable if there's no homomorphism from A to B, no homomorphism from B to A. And again, most pairs of graphs, once you fix a size, are incomparable. Okay, so I think now I can describe to you what is this complete polynomial that we have been harping about. So the polynomial we look at is, okay, this is just a recap of the definition of homomorphisms. So I need to describe the family, I need to describe to you what is G and what is H. Right. So H is going to be just the complete graph. Okay. On the nth graph will have n raised to 6 vertices. So already this looks a bit fishy. I mean, if H is the complete graph, then what do we mean by a homomorphism from G to H? Any labeling of the vertices of G by numbers in the range 1 to n raised to 6. Any numbering. It's coloring, exactly. Yeah. So actually the polynomials we are looking at are just coloring, and it's in order to obtain the hardness that we will have to carefully set some variables to 0 and disallow certain things. So once H is the complete graph, we are just looking at colorings, but we are allowing a large number of colors. Now G it's essentially a complete binary tree, but then we do some massaging. So start with a complete binary tree which has n leaves. If n is not a nice power of 2, then pad it out and so on. Then what do we do with this tree? We inflate it. So at each node of the tree we place a gadget graph. This gadget graph is, so we are going to choose 3 gadgets, and these 3 gadget graphs should be rigid, they should be incomparable with each other. So we do this placement, and then the connections between the gadgets, we stretch them out into long paths. And that gives us a family which we are able to show is actually complete for VP. This is still a bit weird, so maybe here is a picture which describes a little more clearly what's going on. Start with this binary tree, and I'm fixing 3 rigid graphs, I0, I1, I2, I0 at the root. It's not used anywhere else, that gadget. And then after that, at alternate layers, I replace each node of the tree by either I1 or I2. In each gadget, I have also marked 3 nodes as attachment points. So one attachment point goes to the left child, one attachment point to the right child, and one attachment point to the parent. And once I make all these attachments, then these edges from the original binary tree are stretched into long paths. So that's really the graph. Start with a small tree and then plant these gadgets and stretch out the edges. What do these gadgets look like? Here's a picture of a gadget that works for us. This is a graph on 16 nodes. If you look at only the blue and the green nodes, that's the basic underlying graph, and the red node could be placed in any of these 3 positions. And the way these edges are placed, basically it ensures that all the 3 graphs are rigid, and the way the red edge moves around, it ensures that these 3 graphs are incomparable with each other. So this is a fairly small gadget. It has just 16 nodes and lots of edges, and I'm going to place a gadget of size 16 at each node of my n-leaf binary tree. And then I'm going to stretch the binary tree edges into paths of length maybe 48 or something. Okay. So that's the description of the graph G. I wouldn't try to draw the graph G as such with this gadget plugged in everywhere, but the point I'm trying to make is that the polynomial we have finally defined is a graph G obtained using this. H is the complete graph, and take all homomorphisms, and now look at the corresponding polynomial. So this polynomial, it turns out, is it characterizes VP. Why is it hard for VP? This is where we disallow certain projections. Sorry, is there a question?
So, yeah, do you have the quadratic number of vertices in G?
Do you?
What's the order of the number of vertices in G?
In G?
Yeah.
It's order n. Because I'm starting with a binary tree with n leaves, and then I'm just doing this small gadget construction. Yeah. So G is size order n, and H is size order n raised to 6. Maybe it can be brought down to n raised to 4. We didn't look at that too carefully. So in order to show that this is complete for VP, what we need to do is to say that take any VP polynomial, I can express it as a homomorphism between G and H after instantiating these variables by field constants. So the way we instantiate the variables is we set a whole lot of the variables just to 0. So now suddenly H, instead of being a complete graph, if you pick out only the non-zero part, it looks like a very sparse thing. And in fact, it looks like one of those universal circuits. But a universal circuit has also, imagine the universal circuit which Raz has already shown is complete for VP. Imagine planting those rigid gadgets at every node of the universal circuit, and then make sure that your projection picks out a copy of that in H. And then the rigidity and the pairwise incomparability, it ensures that if a homomorphism is going to give rise to a non-zero monomial, the only way it can do that is by actually mapping G to some kind of a tree in the copy of the universal circuit. And the trees in the universal circuit are really parse trees. They correspond to the monomials that the universal circuit is computing. So you can get exactly the computation of the universal circuit after doing this appropriate restriction of the variables. So that's how we show that this family is hard for VP. Yeah?
Is this over all fields? Or
this is over all fields.
so you'll also have to ensure that there's no cancellation, meaning you don't compute the same monomial.
So actually, you could compute the same monomial more than once via different monomials from the target polynomial. No, so what we show is that for each monomial of the target polynomial, there is exactly one homomorphism that can compute. Now, maybe I shouldn't say for each monomial. Maybe what I should say is for each parse tree in the target circuit, there is exactly one homomorphism. And then you could combine the parse trees in whichever way.
Another question, maybe you're going to say this. don't see how the homomorphic polynomial actually has a small circuit. Seems like a big.
Yes, yes. So that's not obvious at all. So this part is for why is it hard, right? Why is it VP hard? Now we still need to show that this is in VP, otherwise the whole point is lost. So why is this easy? It turns out that the graph G which we had, it was a bounded tree width graph, right? We started with a tree and then we put a small size gadget everywhere. So you can start with a nice small tree width decomposition of this graph and actually piece together the polynomial. And in fact, this saying it's not clear why the homomorphism polynomial is easy, but not just for this graph. For any graph G which has a nice decomposition, and let H be the complete graph, the corresponding polynomial will be easy to compute. We can come up with a poly-size circuit for it, poly-size, poly-degree circuit. So it's basically a dynamic programming algorithm. And there's a bonus to doing this membership algorithm this way, and this is also new over the previous result we had with Oracle reductions, which is that the essential property about G we used was that it is bounded tree width. If in fact we had used some other G which was bounded path width, then we could have used the path width decomposition and come up with a way of computing this via a branching program. And that led us to study, can we also get problems which are hard for branching programs using this, and it turns out that that is indeed the case. So we get completeness for many classes here. This is the generic setup, homomorphism polynomials, and to get VP completeness, G has to be the binary tree with stretching and inflation. So that stretching and inflation, let's take it for free every time. To get something which is complete for branching program, I just take a single edge. I plant rigid graphs at either end and then I stretch the edge, so it looks like a dumbbell, okay? And that dumbbell is hard for branching programs. So in the same framework, we get VP completeness, we get VBP completeness. Naturally, one should ask, can we also get VNP completeness? It turns out we can also get that. For this, we start with a cycle and we replace each node by a gadget, and these gadgets should all be rigid and pairwise incomparable. Now here, of course, the gadgets are not going to be constant size anymore. As n grows, you will need larger and larger gadgets, but even then G will be roughly of size n square, not more than that. But you change G, H remains the same, and the polynomial becomes complete for these different classes. Another interesting thing is that you asked, it's not clear why it is in VP, but for all these polynomials, it's not clear whether the coefficient computation can be easily done. So we show that it is in VP, for instance, by doing a dynamic programming, by constructing a circuit via dynamic programming. But if you just give me a monomial and ask me what is the coefficient of this monomial in the homomorphism polynomial, I still don't know how to compute it efficiently. And that's not typically the case with things that polynomials that are in VP. So there is some anomalous behavior here.
You can do it non-uniformly.
Non-uniformly also, I can do it in sharp P, but I don't know how to do it in P. So I would expect that VP polynomials should have coefficient computation in P, and I don't know how to do that. Okay, so the final, the takeaway line here is that we have defined a family of polynomials where defining it did not require you to know what is VP. And then we have shown that it is complete for VP. So that is really the contribution here, that till now we did not have independently defined families which were complete for VP, and now we do. Okay, that concludes part 1. Part 2, I would like to talk briefly about intermediate complexity. So here's this is also an enumerator polynomial, the cut polynomial. Take any graph on n vertices. In fact, I'm going to assume that we have the complete graph on n vertices. Look at every cut in this graph, A and vertices in A, vertices not in A, and multiply the labels of the edges in the cut. So for instance, on 3 vertices, here's the cut polynomial. So this is a fairly standard enumerator polynomial. It is in VNP. What's remarkable about this polynomial as opposed to Hamilton or Hamilton cycle or clique or permanent? What is remarkable is this result which Burgesser proved way back in 1999, which is that over the field GF2, if VP and VNP are different over this field, then this problem is neither VNP complete nor in VP, nor in VP. Unfortunately, to prove that, you need an additional condition. So it's not enough to separate VNP from VP. If VNP and VP are distinct, and if something more happens, parity P does not have poly-size circuits, then this polynomial has intermediate complexity. So it's a strange kind of result which combines something from algebraic complexity, something from Boolean complexity to lead to a conclusion about algebraic complexity. What do we know about results of this flavor? Well, in the Boolean world, Ladner's theorem is well known, and it says that if P is not equal to NP, then we have lots of intermediate problems. In NP, not NP hard, not in P. And Burgesser basically answered this, did the same thing in the algebraic world over every field. If VP and VNP are distinct, then there is a polynomial family which is intermediate between VNP and VP. But both these proofs, basically they demonstrate the existence of an intermediate problem, and that existence is demonstrated using diagonalization. So the cut polynomial is remarkable because this is only over a specific field, not over every field, but it's an explicitly defined polynomial, and we know that it is intermediate under this additional assumption. In the Boolean world, we really don't have an analog of this, an explicitly described problem which, if P and NP are distinct, then here this is the problem which is intermediate. We don't know anything like this. So this is something which we know in the algebraic world. What about over other fields? Well, this same polynomial cut over other fields is not intermediate. Over reals, for instance, we know that it is VNP complete. Over other finite fields, Burgesser again showed that these a variant of the cut polynomial, you just raise everything to power q minus 1, then these polynomials are all intermediate. So all this work was done by Burgesser in 1999, and then he asked whether there are other intermediate polynomials. What is it that goes into showing that a polynomial is not too hard but not too easy? So that's where we did something. We came up with a definition of, we came up with proofs that some more polynomials are intermediate. And in order to get there, we had to look at why some polynomials are hard. Why is Hamilton cycle hard? Why is clique hard? The monomials of these polynomials are encoding some hard to find objects. So what we want to do is we want to put more information into the encoding. By putting more information, it makes it easier to find those objects, but it should not make it too easy, because then you would fall down all the way to VP. So here's a whole bunch of polynomials based on clique, vertex cover, closed walk, three-dimensional matching, satisfiability. For all these problems, what we did was we figured out some amount of redundancy that we can put into the polynomial. So define the encoding in a slightly different way, and this redundancy made it easier than the VNP complete class, but it was not enough to make it easy for VP. So just to give you a flavor of this, I'm going to show you how the clique polynomial was redefined by us. The original clique polynomial is you just take every clique and there is a monomial for it. So for every if you're dealing with the complete graph, then for every subset A of the nodes, there is a clique sitting on those nodes in A, and there's this monomial. Instead of viewing this from the point of view of vertices, let's view it from the point of view of edges. For every subset of the edges which defines a clique and an isolated set of vertices, you have a monomial. And this is what we relax when I say that we are going to put in more redundancy. This part is exactly what appears there. For every subset of the edges, there is a monomial. But this monomial should not even have been there if this subset does not correspond to a clique, and it is not there. Here we allow this monomial, but we pad onto it something which probably looks like junk. It's not really junk. It's telling you which are the vertices that are touched by these edges. So given this additional information, you look at a monomial, you know whether it corresponds to a well-defined clique or no. So it's made things easier. It's not going to be as hard as clique. It doesn't make it too easy, so it's still not going to be in VP. The concrete example here, for the empty set of edges, both of them have the monomial 1. For the full set of edges, the original polynomial just had the x variables. Here I have the x variables and the y variables, and the difference is here. So if I look at the edge set 1, 2, 2, 3, this is not a clique at all. So it does not have any monomial in the original polynomial. But here I will still include this edge set, and I will add on this identifier tag which tells me this. And these identifier tags are crucial. They allow us to proceed. So why are these polynomials intermediate? For any of these polynomials, clique as well as such redundant versions based on the other problems, we need to show that it is in VNP. This part is easy in all these cases. We need to show that it is easier than VNP complete. That's what I mean by ease. It's not VNP complete. So in order to do this, we show that actually the polynomial can be evaluated in Boolean P. So if it can be evaluated in Boolean P, then it had better not be VNP hard, because then if it were also VNP hard, then parity P would have these small circuits arising from that Boolean circuit. To show that it is hard, to show that it is not yet in VP, we will need to show that the monomials are actually still encoding information about a sharp P complete problem. So if this were all the way down in VP, then parity P would have small circuits. So in either case, we need that extra assumption that parity P does not have small circuits. But now this is the point where these two statements seem to contradict each other. We are saying that H can be evaluated in P and H is not in VP. So in fact, to me, this really further drives home this distinction between P and log CFL. VP is not the algebraic version of P. VP is the algebraic version of log CFL or SAC1. So this H is not in algebraic log CFL, but it is in Boolean P. Boolean P is a much larger class. So the algorithm here, although it is a poly-size circuit, it is not a poly-degree circuit. That really makes all the difference. Okay, so I have a slide here describing why this is intermediate, but let me skip this and just move over to the third thing, because these three parts are all related. We are trying to understand completeness and reductions amongst polynomials sitting in between these classes. So the first part was motivated by trying to find something which is complete for VP using only P projections, because that is the right notion of reductions when you are looking at this class. And now one could go further and say that why just P projections? You may want monotone P projections, because in the Boolean world we have very nice lower bounds for monotone computation. Do we know exactly how to lift them in the algebraic world? Well, we do have lower bounds in the algebraic world as well. So now, keeping these two things in mind, what more can we say about monotone projections and completeness? So here our focus has now shifted to V and P. Okay. So monotone P projections. These are more restrictive than P projections. In P projections, remember, you are allowed to instantiate variables by other variables or field constants. Now you can instantiate them without using negative constants. So of course we have a totally ordered field and you're not allowed to use negative constants. So in this setting, what we want to know is, well, okay, why do we want to know anything at all? Permanent is again a very good example to go back to. Well, we could get better lower bounds for monotone Boolean circuits for the permanent by showing that certain polynomials are not monotone projections of the permanent. Okay. Is there a problem with this one? Yes, of course, of course. So these are the bounds that we know. The best lower bound is really n raised to log n. It's not, it's nowhere near exponential. One would like to try and push it to exponential, for permanent. So what Jukna observed.
Not permanent. This is just matching. Really.
This is just counting matching.
Not counting. Not counting. The lower bound is not for counting. It's even for deciding whether there is a match.
Yes, and therefore it's also for counting.
It's also, but it's maybe.
No, the point is that for counting, somehow I mentally expected that there would be an even better lower bound, a larger bound, because you are asking for even more information.
I don't know that it was us, but you would want a threshold version, right?
Yes.
Other at least.
Yes.
I don't know that anybody looked at it.
And I think they have.
Razborov didn't look at it.
No, Razborov didn't. So I think Jukna had been looking at this too.
Okay.
Yeah. But I think finally this statement that Jukna is making is again about deciding. That's true. That if the clique polynomial or the Hamilton cycle polynomial is a monotone P projection, polynomial projection of the permanent, then we can push this lower bound of Razborov from quasi polynomial to exponential. Yeah, but this is again, I agree, it's for deciding, not for counting. Okay. So therefore, this is a good motivation for asking whether, so we know that the permanent is complete for V and P. So the Hamilton cycle is a P projection of the permanent. Does that projection really require negative constants? The standard projections that we know do use negative constants, but maybe there are other ways of doing this. So Grochow showed soon after this that any monotone projection from the permanent to the Hamilton cycle, it does require an exponential blow up. There is no way of obtaining the Hamilton cycle from a small permanent. But really we would want this kind of a statement for a clique, and this, so that is the thing that we showed. Any monotone projection, any way of obtaining the clique polynomial from the permanent using a monotone projection must involve an exponential blow up. And in fact, this same strategy also works for two of those polynomials which earlier were shown to be intermediate, satisfiability and another polynomial based on closed sequences, closed walk sequences. Those were polynomials which are intermediate over finite fields, but here over a totally ordered field, they cannot be written as small permanents, as small monotone permanents. Okay. And how does this proof go? Well, you look at the Newton polytope associated with polynomials or with solution sets. For any polynomial f, Newton f is the convex hull of the exponent vector. Take every monomial in the which appears in the polynomial with a non-zero coefficient, write out its exponent vector. So these are points sitting in the appropriate n-dimensional space, and just take their convex hull. So, so some measures for the polytope. Well, you could talk about how many linear inequalities are required to define the polytope, or you could also talk about its extension complexity. Maybe the polytope Q itself requires a lot of inequalities to be defined, but sits inside some higher dimensional polytope which is compactly described. So these are some measures. And what Groucho showed was this very nice result, which is that if f is a monotone projection of G, then the extension complexity of the Newton polytope associated with f is at most the number of variables in G plus the regular complexity, not the extension complexity, the complexity of the Newton polytope of G. So using this, we were able to get the lower bound for the clique polytope. The permanent polynomial, it can be described very efficiently. You just need to say that all row sums and column sums are 1. So order T inequalities is enough. And for the clique polynomial, we showed that its Newton polytope actually extends the correlation polytope. And for the correlation polytope, we have this recent very nice result which says that its extension complexity is exponential. Putting all this together, Groucho's result, the extension complexity of correlation and so on, we conclude that clique cannot be written as a monotone projection of a small permanent. So in some sense, it's saying that the permanent, even though it is hard for VNP, it really crucially relies on cancellation. So on negative constants and cancellation. So this also I found particularly ironic, because when we were studying the small space classes and determinant, why is the determinant easy? Because you can do cancellation. Why is the permanent hard? Because you cannot do cancellation. And here it seems like the hardness of the permanent is relying on cancellation. Without that cancellation, it is not really hard enough. That's what it looks like. So it's something which is curiously contradictory in nature. Oh, I'm actually done. Yeah. Okay. So the same strategy also works for satisfiability, for showing that the satisfiability polynomial is cannot be written as a small monotone permanent. Here we use the this lower bound due to Avis and Tiwari, which is that there are formulas for which the associated polytope requires exponentially many inequalities. For the another intermediate polynomial which I did not even describe fully, based on closed walk sequences, the natural polytope to use there is a traveling salesperson polytope, which is embedded inside its Newton polytope, and we know that this has high extension complexity. So here are these two other polynomials. So the clique polynomial, so now we know several polynomials, the Hamilton cycle polynomial, clique polynomial, satisfiability, CLO, all of them require large permanents if you do not allow negative constants. So to me, this kind of suggests that maybe one needs to re-examine this permanent again from the point of view of cancellations. It's not that everything about it is known and settled. It had not occurred to me till this work that the negations could be useful for hardness. To me, all along cancellations were useful for giving upper bounds. So
but there's a confusion in what you say, because
yes.
The permanent just has positive coefficients. It's not hard because it doesn't have negation.
No, but not that the permanent is hard. That does it have enough? Is it rich enough to capture other computation? So there, yeah, we need these negative constants. No, okay, I get what you're saying. So the polynomials which I'm trying to express as the permanent also do not have negative constants. Yeah. So it's
possible that all the pairwise have this property.
Yes. So that's exactly what seems
so
to be.
It doesn't contradict something else.
No, it doesn't contradict. But to me, it was kind of pointing study towards a different direction, which I had not thought of before. So in the monotone world, it was very clear that these negations play a role, because we have this wonderful proof by Rasburov. But in this setting, I had not thought of it this way at all. That even to obtain a reduction, I would need to use these negative constants. Okay, so to summarize, here are these three types of results that I described here. One was completeness for algebraic classes based on homomorphisms. Then the other was intermediateness, and then the third was about a particular kind of reduction, monotone projections, and a lower bound in that setting. So all of these results are basically about completeness and structure and reductions. And this is something also which some earlier papers by Eric, which I was much inspired by. So in particular, arithmetic classes, there's this survey which we still go back to very often, the survey which you wrote, in which there was this description about why you would expect things in the arithmetic world to be easier. They are more powerful, but they are weaker, their hands are tied. So that was something which that idea I carried forward in a lot of my work that I did later on. But this in the algebraic world, so I started looking at the algebraic world only in the last 5 or 6 years, and really what set me off was Eric's result about width 2 branching programs, that they could not do something. And why would it be so hard to prove that? That was one result which even now I feel the result is completely obvious. It cannot be false, it has to be true, and it's amazing to me that it requires such a hard proof, that here is an width 2 branching programs in the algebraic world are not universal. So a carefully crafted, carefully structured proof, which I saw Eric and his co-author Wang do, and after that I have been doing more and more of algebraic complexity. Okay, so with this, let me conclude my talk. Thank you.
Questions?
Like the reduction from the, so the question is whether you can reduce the permanent to the determinant. Is the reduction from the determinant to the permanent, is there a straightforward one, or do you really have to go through all the machinery?
Not very straightforward.
Okay.
Not very straightforward.
Do we know anything about all sorts of naturally defined combinatorial polynomials like chromatic polynomial, Tat polynomial, matching polynomials? Did anyone manage to place them anywhere
in these
higher?
classes? So I am not very familiar with these polynomials, although I have heard talks about them. But most of the interesting cases seem to be with very few variables. And that becomes a barrier to allowing them to characterize classes.
The same way, you know, you have you take colorings with into the 6 colors, then you might do the same thing.
No, not polynomial.
But
It's a
polynomial is
two-variable
by way.
polynomial. It cannot be hard.
No, but it has cousins with many.
Yeah. Then they are
yeah,
sort of
yeah,
hard,
yeah.
many of them. Yeah, it's not. Like
It is.
that.
So they are sharp. They are sharply
Well,
hard to
sharply,
compute.
but I think they're also
So they should
VNP.
also be VNP hard, but I have not seen those.
You associate a verb with every edge
Yeah.
and you do the same thing.
So typically the combinatorial problems which are sharply hard, their algebraic versions are VNP hard, whereas this thing seems to break down at VP, what is complete for VP. But I have not looked at them closely.
So you had the polynomial that you were able to show that was sort of intermediate, assuming some specific polynomial didn't have small circuits, right? This these parities.
No, so the class parity P. Parity P. So the polynomial which I described would have been is intermediate between VNP and VP over the field of characteristic 2, unless you can count the number of satisfying assignments mod 2 efficiently. That's one way of putting it. So if you can count mod 2 efficiently, then we don't know about intermediateness.
So is it? I guess I'm wondering if you could prove something like this with a weaker assumption that you could do some less specific thing efficiently.
So this is what we seem to need in our proof. But it's not. We are not talking about a specific polynomial. We are talking about this complexity class. The entire class is going to collapse to polynomial size circuits. But both are directions, intermediate as in not so hard and not so easy. Both of them seem to require exactly the same thing. So it seems to suggest that that would be the right requirement.
Which of the current approaches to separating VP and VNP you think will be, or is your favorite?
I don't have a. What I can say is the geometric complexity approach I don't understand at all. So that is clearly not my favorite. But so there's a lot of optimism based on the lower bounds following depth reduction and structural results. So I don't know enough to say whether that is the most likely one to lead.
And you can find an algorithm for PIT.
PIT.
That's another
Yeah.
one.
So between PIT and structural reductions, I don't know. I don't have a favorite.
Okay, thank you.